Hello, my name is Yashish Gotipati. I'm a first-year master's student at the University of Utah, and the paper that I'll be presenting today is titled FedRAN, Federated Mobile Edge Computing with Differential Privacy. So for the problem setting, we've seen in recent years a rapid increase in access to powerful compute. Things like AWS and Google Cloud allow you to just spin up compute nodes whenever you want. Also, with recent advances in mobile endpoints, such as like the iPhone 12, we have these massive amounts of compute just on these small smartphones. Also, with like 5G and these next generation architectures, we have more users and types of devices entering the network. And there's two sort of consequences that arise from this. The first one being data. So with more devices in the network, we have more data being generated. And Cisco actually estimates this at roughly 850 zettabytes at the mobile edge by the end of 2021. And to put that in perspective, global data centers are currently estimated at roughly 20.6 zettabytes. On the other side, we also have an added layer of complexity, and this is due to more types of devices, such as IoT and mass machine type. We also have more users, and then you have things like network slicing and software-defined networking, which enable more dynamic networks. So to handle this added complexity, we've seen a move towards these data-driven software-defined networks, things such as ORAN. And what these enable is the ability to adapt in real time to these sort of dynamic networks and environments. And the examples I have here are quality service slicing and mobility optimization. So an example here would be you can represent the area which a device can move with a probability distribution and use that distribution to inform how you optimize things such as handovers. So then the question that we looked at was, can we utilize the massive amounts of edge compute and edge data to help realize this data-driven network? The answer is yes, but there are many caveats, and the main thing being privacy. So with using machine learning and these things, who has access to the data and how that data is handled is a big concern. And this is actually a headline from a recent news article expressing just this. So continuing on, to realize an intelligent edge like this, we need to maintain a high level of endpoint privacy. And this also comes from legislation from like the European Union's General Data Protection Regulation, which does place constraints on how data can be collected and how data can be used by certain entities. Also, from an engineering perspective, transferring all this mass amounts of edge data over the network doesn't make much sense either, just because of network congestion and network constraints. So the problem that we specifically explored was, is there a way that we can learn without explicitly transferring the data? And the answer is yes, and that's what FedRAN is. It enables the ability to tap into the vast amounts of edge compute and data without compromising privacy. And this is an effort to enable this large-scale sort of edge computing ecosystem. Okay, so the first pillar of background information is federated learning. So federated learning, put simply, is a distributed method for training a model that does not require the IID data assumption. IID stands for identically and independently distributed. So with most machine learning methods, you require data that's drawn independently from the same distribution. However, for federated learning, you don't really need this assumption in practice. So what federated learning is you have a bunch of endpoints. Each of these endpoints has their own local data sets, and each of these endpoints will train their own local model, and then all the local models will then be aggregated together to produce a single global representation of the underlying distribution. So there are a few benefits of adopting a federated learning architecture. So the first one is that it enables an access to the vast amounts of edge data without straining endpoints. And also there are some privacy benefits, because in federated learning, you're not actually transferring the local data over the network to get this global representation. You are only transferring over the model weights. And also the federated learning architecture can be adapted to support a variety of different levels of compute. So the idea here is, if you have a legacy smartphone or a weaker endpoint that's not able to fully train a local model, then the idea is you add an intermediary node that would train the remaining portion of the model that the legacy endpoint cannot finish. So then at that point, the intermediary node would finish training and then would send that local model to the central server for the aggregation process. However, with federated learning, there are still, again, its own shortcomings, and this is why we use differential privacy in our work. And so the main point of attack with federated learning is this attack known as the gradient inference attack. And so on the left-hand side, we can see a case without differential privacy, and this is where a gradient inference attack is likely to occur. So in a real-world setting, you have your model, you have live data coming into your model, and then you have predictions coming out. So this adversary, represented with the blue smiley guy, is able to sniff these prediction packets. And so if the adversary is able to sniff enough prediction packets, then they can sort of infer gradient information about the model and the live data. And if the adversary is able to infer this gradient information and possibly reconstruct a portion of the live data set, then it's possible for them to also take that information and use it to infer or gain access to sensitive information. And so on the right-hand side, we actually have a case where we employ differential privacy. And in this case, we can see that the adversary is confused. And the reason for this is that differential privacy seeks to obscure the gradient information. So to the adversary, when he's sniffing these packets, it looks like these predictions are coming from different model distributions or different live data distributions. So essentially, the adversary is not able to infer this gradient information. And so more formally, we have this inequality here that represents differential privacy, but it boils down to saying that the probability that the output distribution of a model differs on a single element from data X is bounded by this exponential function on the right-hand side. So on the right-hand side, you have this exponential with an epsilon in the exponential, which is referred to as the privacy budget. And because if the privacy budget is larger, that means you're willing to leak more information. And you can see this because the exponential would be larger on the right-hand side. If your privacy budget is smaller, that means you're willing to leak less information. So the probability is bounded by a smaller value. And the delta term is referred to as the error tolerance. And also, to inject this noise, you can't just inject any random noise. You have to use some sort of privacy preserving statistical techniques. And there are examples written here below, such as Laplacian, exponential, and Gaussian sampling mechanisms. And so now I'll touch on FedRAN. So FedRAN follows a generic federated learning architecture. So on the right-hand side, you have the different endpoints, which are those red squares. You have the local models and the global models, which is represented with the green squares, and the central server, which is represented by the blue PCs. So how the procedure works is that you have a global model that's bootstrapped to the endpoints. The endpoints then train that model locally on their data set. And then once the endpoints finish training, they then send the model updates, so the new model weights, to the central server. The central server then aggregates these weights together using like averaging or some other technique. And then the central server will then bootstrap the endpoints again for another round of training. And this is done until you reach your desired threshold. So how we implemented this was we used IBM's Federated Learning Library to handle the network interactions between the clients and the central server. We then configured FedRAN to run over the SRS LTE network. And we implemented a differentially private stochastic gradient descent algorithm with TensorFlow. So here's the use case from our paper, and specifically it deals with smart vehicles. So in the figure below, we have a traffic cone which represents an unknown foreign object to both vehicles. So car 2 encounters this traffic cone, and so this encounter is encapsulated within its local data set. And so we have the federated learning procedure where this local data set is used to train the local model, which is then aggregated into a global representation and then shared to car 1. So later on, when car 1 encounters this traffic cone, it's actually able to deal with it because it's able to learn from car 2's experience. And actually what's cool is that there's a similar framework that's already employed at Tesla for their full self-driving beta currently. And so now I will cover the evaluation. So here's our setup. So we used Powder's controlled RF environment. We used IBM's federated learning agents that were deployed on the clients and the central server. And we deployed the server at the edge using the SRS LTE eNode B. So we deployed the server at the eNode B, so it's technically at the mobile edge. We also utilized the MNIST handwritten digits dataset for our proof of concept. And so our training procedures, we implemented a convolutional neural network with TensorFlow. We utilized the categorical cross-entropy objective function, and we used stochastic gradient descent with and without differential privacy. We set the global termination classification accuracy to 90%, meaning that when the global model reached 90% accuracy on its test set, then the training procedure would halt. We also required all clients to participate in each communication round. In reality, you'd have a fraction be required to participate because of mobility and other factors that can influence a client's ability to finish the training procedure. And so our first evaluation compared a local model to a distributed model. So how we did this is we first modified the client training data by removing entire classes. So on client 1, we had removed 3 different numbers. On client 2, we removed 3 other numbers. And so what this emulates is a situation where both clients only have a partial view of the underlying data distribution. And then we trained the CNN locally and distributively for different epoch settings. And then we just recorded different metrics to quantify our evaluation. So here's our results. So on the left-hand side, we're looking at the classification accuracy versus the total epochs. So in the y-axis, we have the classification accuracy. On the x-axis, we have the total epochs. And so the bluish colors represent the locally trained models, and the yellow and orange represent the distributed models. So we can see as the epochs increase, the distributed models continue to do better and consistently outperform the local models. And intuitively, you can think this is because distributed models are able to learn from each other. So client 1 is able to learn from client 2's dataset, and client 2 is able to learn from client 1's dataset. And this allows the 2 distributed clients to better classify examples that aren't in their own dataset. And along the same lines, on the right-hand side, we have the loss versus the total epochs. So on the y-axis, we have the categorical cross-entropy loss. X-axis, we have the total epochs. And again, we see the similar trend with the distributed clients outperforming the locally trained models. And this is because the distributed models are able to learn from each other and are able to classify examples not within their local client data set. And so for our second evaluation, we looked at different differential privacy settings. So we varied the different privacy budgets. We trained the CNN for 60 epochs, and we also ensured that clients had access to all the image classes. And so here are our results. So on the top left, we have a setting with no additional privacy. The bottom left, we have a large privacy budget of 0.5. Top right, we have a smaller privacy budget of 0.5. Bottom right, we have a privacy budget of 0.3. So again, the privacy budget refers to how much information you're willing to leak. So a larger privacy budget refers to that you're willing to leak more information, and a smaller privacy budget means that you're willing to leak less information. So with a smaller privacy budget, you inject more noise because again, you're trying to leak less information. So on the top left, we see that the graph is further to the left and up, and this essentially means that it has the smoothest convergence and fastest convergence, and this is because no noise is injected. And then in comparison to the other graphs, we see that as more noise is injected, so as the privacy budget is decreased, we see that the convergence becomes slower and becomes less smooth. And so in summary, we presented and validated a differentially private federated learning system at the mobile edge. To enable this sort of privacy-preserving large-scale edge computing ecosystem, we exploited the advancements in compute to help realize a data-driven network. And we also packaged FedRAN as a powder profile to help enable others to explore applications of federated learning within a real RF setting. And so here are my references. And thank you for your time. Questions are welcome.